Hallo, dieser Podcast wird Ihnen präsentiert von der Hannover Messe. Viel Vergnügen beim Zuhören.
Hallo liebe Zuhörerinnen und Zuhörer, willkommen zu einer neuen Kurz KI Folge KI in der Industrie, Folge 90. Mein Name ist Robert Weber und ich habe heute eine super spannende Folge mit dem Jonathan Masci für euch. Und Jonathan ist Co-Founder bei NNAISENSE und wir sprechen über Windkraft, Drohnen und Deep Learning. Hallo Jonathan.
Hallo Robert.
Gib uns doch am Anfang mal einen Einblick in euer Windprojekt.
Sure. So the project is aiming at the use of AI, artificial intelligence, for detecting damages from optical inspection of wind turbines. So basically what you have is a drone that collects images from the turbines. So you have these gigantic blades that get recorded from the drone, and then you have images that you need to look for defects. So this can mean anything from some grease that maybe it's not important to structural damages that require the blade, the turbine, to be stopped. And obviously, if you can monitor really well, you can minimize the downtime operation of the entire turbine farm.
Okay, ihr überwacht die Blätter der Windkraftanlage, aber ich kann doch diese Blätter auch über eine PLC, über eine SBS, über Sensorik detektieren und rausfinden, wenn was nicht smooth läuft, wenn im Prinzip ein Schaden auf den Blättern ist. Warum nutzt ihr keine SBS?
Certainly that's something that you can do, and it is done indeed, to detect certain types of damages. Let's say a thunderstrike or something like that. But what we at NNAISENSE are looking at is visual damages. So it's an optical inspection. We are looking for cracks or scratches or damages that can lead to other types of issues with the turbines.
Okay, also ihr habt eine Drohne, die macht mit einer Kamera Fotos, die Kamera kommt zurück auf den Boden und dann fangt ihr an, die Blätter zu untersuchen.
Yes, that's correct. So the drone has a flight path that is followed. So it's a consistent data acquisition pipeline. So you get pretty much constant distance from the blade, and the quality of the images is pretty high. We're talking about each image of more than 5,000 pixels on the shortest dimension. So it's, I would say, beyond what you commonly see in deep learning applications in computer vision. So you get all of these images. And then all of these images get sifted through the AI detector that we developed, and we provide annotations. These annotations are pre-annotations, so they're sent in the end to some front end for the expert user to finally give another look at the images. This is more of a requirement from let's say it's a compliance requirement. Obviously, the AI could do everything by itself. But the human in the loop gives a certain level of extra safety, because it's important to remark that this is not a toy problem where we try to find something funny in an image. You don't really have to miss anything critical. And so this is at least at the beginning what we are looking for.
Welche Daten braucht ihr? Habt ihr verschiedene, wie soll man sagen, Schadensfälle oder verschiedene Schäden, die ihr definiert habt, um das Modell zu trainieren?
Yes. So in this way, it's a deep learning problem. So you have, on the one hand, a lot of data. In our case, it's a supervised learning problem, which means that for every image, we are provided with an annotation. Let's say through the years, this work has been done by expert users. They annotated a lot of images in the order of terabytes of data that has been collected. And the role of the AI is to distill this knowledge of the users that is encoded in the input and target representation into the weights of the neural network. And this is done by algorithms such as gradient descent and so forth. And the model that we use is a single stage detector. It's a convolutional neural network model, which is one of the best possible uses of convolutional networks, obviously, is for images. So you get a backbone that tries to understand the important features of the image. And then you get another component that is providing with potential areas of interest, which are many, let's say in the order of 100,000 of those. And for each one of those, you have two additional networks. One network that produces the bounding box regression, which is really the rectangle that you would draw on top of the image, and you want it very tight to the damage. And then you have another neural network that performs the classification. So not only we can detect, but we can also assign a label to the defect.
Mhm. Wie kommen neue Schadensfälle in das System?
So the damages in the context of supervised classification are assumed to be always the same. And the technology that is provided at the moment needs to cover these defects. In case new damages are to be presented to the model, then there are different strategies, but this is not the case. Usually these damages are codified and there are certain standards to basically determine what constitutes a defect. Obviously between different providers, you may have a little bit of discrepancy, but as long as we have enough data to train, that's no problem. And especially once you have a very good, and that's what we have actually, trained model that performs with high accuracy on the task. If you have a new damage, then you can easily transfer with a, let's say, smaller amount of data representing that new damage.
Okay. Jetzt trainiert ihr das System in einer Cloud, in einem Rechenzentrum, wo auch immer. Warum spielt ihr das System, das Modell nicht direkt auf der Drohne auf, sondern auf der Station oder am Boden? Ist das technisch eine Herausforderung, problematisch?
Well, I have to say there is nothing that prevents us from deploying the AI on the drone itself. This is simply something that is not in the requirements of this project, so we didn't have to do that. And this obviously gives us the freedom to explore maybe more heavier models in terms of computational resources. But in terms of the use of, let's say, the model directly on the drone, I would see the need of doing that only if there would be a way to make use of the model while flying the drone. Mm-hmm. Or, for example, if one had to take decisions while doing the inspection. For the second case, this is never happening, because obviously if there is a damage, anyway, you have to wait to do anything. But for the other point, obviously, if the drone had to be flown by AI, then that would be a different problem.
Okay, also es wäre möglich, habe ich verstanden. Aber was mich interessieren würde, es wäre doch super, wenn die Drohne ein Foto macht und es könnte direkt mit der Windturbine verbunden werden. Und angenommen ist ein Schaden und dieser Schaden könnte minimiert werden, wenn man dann die Anlage etwas langsamer fährt oder sofort stoppen. Wäre das nicht ein sinnvoller Ansatz?
There are certain applications, and this is actually looking already forward to the next steps of this project. So you can think of use cases where, for example, you're flying your drone and then the drone takes a picture and that picture is not high resolution enough because the defect is very small. And so you have a high uncertainty in your model to determine whether there is an actual damage or not. Or maybe the class is not clear. So what you could do in that case, you could have the drone fly closer, take another picture, and then better assess whether this is an actual damage. And this is something that is under discussion, actually. But I would say, as with everything, right? So we want to deploy AI and we want to do it in a reliable fashion, which means that we need to have something off the ground that works and that we can trust. Then all the rest, obviously, that's something that can come later. But, in order to finish you first need to finish, right?
Wie viele Bilder macht ihr von den Blades?
It's in the order of 300 pictures. And so each one of those pictures is localized within the blade itself. So you can think of a very nice charting of this blade with a lot of pictures on top of it. And in fact, this is visualized in this way. This is through our partner, Sulzer and Schmidt, who's providing the drones and the interface for the inspection. And the AI is making use of all of these images to better assess what constitutes a defect. Because there are certain areas that are more prone to defects. For example, the tip or the edge. the leading edge. And obviously, if you know where that picture comes from, you can make a different assessment with respect on what's more likely to be a damage in that area.
Okay, ich habe das vielleicht nicht richtig verstanden. Nochmal, wie viele Bilder von den 300 Bildern nutzt ihr wirklich? Weil Deep Learning braucht ja viele Daten.
So obviously, this should not be mistaken. This is a inference time, which means the model has been trained, and then you're looking at 300 pictures taken from the blade.
Okay.
What you usually do, and that's the training stage, you're provided with thousands of images. As I said, it's the order of terabytes of data. And then you have a training stage. What it means, you go through all of these images several times. Each time you visit all of the images, you call it an epoch. And then after your model has been trained, it's kind of converging to a solution. Then you take that model, you freeze all the weights, and then you deploy that model to be used in production. And what you can do, obviously, is to say, okay, I fine-tune the model because maybe something has changed, or I have, another wind farm that is slightly different. Maybe I want to get, squeeze out the last performance I can get. But in general, there is a clear distinction between what is a training stage, which requires a lot of data, and what is the inference. And at inference, you have a function that, given an image, provides you with annotations.
Jetzt habt ihr das Ergebnis. Und mich würde halt interessieren, ja, du hast ja gesagt, ihr nehmt auch den Domain-Experten nochmal mit rein. Wollt ihr auch wissen, warum da ein Fehler ist? Also wollt ihr auch eine explainable AI machen, warum das System dort einen Fehler detektiert hat? Ist das ein Ziel für euch?
I would say we're interested in explainability in general, because you would like to know what triggers a decision. But given the domain here, I would say that the most promising next step in terms of explainability would be to model the damage and the degradation of the blade over time. Now, let's say that you take for the same blade a picture every month, and then you see the evolution of a tiny crack. And obviously, if you have enough data, what you can do, you can build a simulation of how this would behave in the future, right? And if you have that, then you can explain that, okay, this little crack, thanks to our, what we would call at NNAISENSE a third generation digital twin, will look like this in 6 months. And if you have that, obviously you can, do predictive maintenance. You can schedule all of your repairs. So this is really where I see the next big thing in the wind inspection.
Okay. Also das ist der Plan für die Zukunft.
That's planned to do predictive maintenance this way, yes.
Jetzt sind ja Schäden oder Probleme unterscheiden sich auch und die klassifiziert ihr doch, oder?
So at the moment, as I said, we provide annotations and classification. Obviously, the number of classes or the type of defects that we classify is provided as a binding, as an annotation that says, okay, this is class number 5 and it's called, vertical crack. But nothing prevents us from using different labels. And actually, what the deep learning model is doing is to extract features that are representative of defects, of anomalies in these blades. So you can think of having a backbone plus a lot of extra heavy lifting deep learning models that are converting the image into something that is very easy to work with. And then what you have to do if something changes is to adapt only the final part. That's very common in the industry as well.
Jetzt sind wir schon voll im KI-Thema drin, aber ich habe noch eine vielleicht triviale Frage. Wie schwierig ist es eigentlich, die Drohne so zu kontrollieren, dass sie aus dem richtigen Winkel die Bilder macht, die richtigen Bilder macht?
Yeah, on this we're lucky, and this is one of the strengths of this project, because our partner has a standardized acquisition process. So the drone flies along a certain path that has been standardized, and given that everything is pretty much static during the acquisition because the blades are not moving, this is very consistent. The only thing it doesn't cover is this active component that I mentioned earlier. But at the moment, for the application of AI to detecting and annotating, this is more than sufficient. And actually, this is the enabler for powerful deep analytics, I would say. Because if you have consistent data, then you can really unleash the powerful deep learning that we have at NNAISENSE.
Okay, ihr baut jetzt also als NNAISENSE eine Software, ein Software-Kit, eine Anwendung, oder muss ich als Kunde immer wieder zu NNAISENSE kommen, um das Ergebnis zu bekommen?
So we serve the model as a software as a service on the Azure platform. So this has been integrated. So it's a service that they are using. And I have to say that this is a highly customized solution that does not originate only with this project, but actually I have to say originated with my PhD, because during my PhD under Professor Jürgen Schmidt-Huber, I was doing defect detection for heavy industry for ArcelorMittal. So I was looking at a lot of images from the steel production, and I was the first to ever apply deep learning to that problem. And obviously throughout the years, we at NNAISENSE, further developed it, and now we really have a cutting edge solution for this type of inspections.
Wenn du jetzt mal zurückblickst auf das Projekt, was war von deiner Seite das Schwierigste?
Well, as with any AI project, obviously you plan and then you have to often pivot to certain, to smoothen some rough edges on that you encounter on your way. I would say in this project there are two main aspects. One is the annotation or consistency in the annotation, and the scarcity of data that is representative of defects that really matter, because that's something that obviously cannot be controlled. And it's fair to say that there is less than a fraction of a % of defects that are really, really serious. And obviously you cannot go and fabricate damages, because first of all, you don't know how to do that. And also you would be destroying the blades. So this is what we have to live with. So we have a lot of data, but the data that really represents what we're after is not that much. So this was a big challenge. We had to develop a new type of loss function and data augmentation techniques. So a data augmentation technique is basically a way to fabricate more of the data that you need for your problem so that your deep learning system works better. So this was a big part of of our effort. And then the second, which is less related to deep learning, or let's say the more research that we have to do, more on the research that we have to do, but it's really how to integrate it well. Because I think it's important to understand that even though one might be tempted by, taking an off-the-shelf solution that I would say nowadays you can download from the internet pretty easily, what really matters is how you execute on that. And so how to make it reliable, how to avoid the misses, how to, have a number of false positives, which is reasonable without having, too many misses, because obviously you don't want to have something that has annotations everywhere, then it would be perfect, but obviously the end user would have no use of that. And at the same time, you don't want to miss anything that is important. And striking the right balance between these two components and making sure that the system is stable and usable is really where we come in. And I would say there is no off-the-shelf solution for that. This is the expertise that, has matured over years and years of running this kind of projects.
Okay, du hast gerade gesagt, edit missing data, also du hast fehlende Daten und fügst die an. Wie habt ihr das gemacht?
So I can say that in analogy to that, you can think of, for example, moving the image or changing a little bit the colors. That would be what you would do in image classification. Now let's say that in defect images, what you can think of is a way of adding a new defect on top of another image. So generating. This is, I would say, a very hard route. We opted for something that is a little bit different than that. It's a mixture of resampling and loss design with consistencies on what you expect. But that's, part of the secret sauce. But in general, you can think of doing this type of data synthesis by having a function that generates the data, right? So you can think of a generative adversarial network, for example, that generates the data, or you have some variational autoencoder that fabricates new data. There are a lot of techniques, but it's important to note that these techniques, even though they have amazing results, all of those results are not real. And in industry, you want something that works all the time and it doesn't rely on something that is fabricated purely, right? So we need to always be careful on how we do this kind of things. And this is really the main effort in making things usable, to deploy an AI that you can trust.
Und wie immer, was sind die nächsten Schritte bei euch in diesem Projekt?
So I would say the more imminent step is to make use of what we have and build a degradation model, so predictive maintenance. That's really where I see this moving next. And then the drone, obviously, that's up for discussion. From NNAISENSE, there is nothing that we see as a stumbling block in trying to fine tune this flight path to be more appropriate for certain usages. And maybe another thing that is very important and that I think it's essential for this to be deployed and to gain strength over time is that every time, obviously, you do an inspection, and now inspection time is down instead of 1 hour that it's usually taking for an operator to do the inspection of a wind turbine to 20 minutes. So it's a drastic reduction of time. You can gather much more data. You can scale. And so this means that you have more data to train. So if you keep pre-training and retraining on more data, the more you do it, the better you become. And so also the usability of the system will benefit from that. So this is a human-in-the-loop data bootstrapping, we call it.
Dankeschön, vielen, vielen Dank, Jonathan Masci, für diesen Einblick zum Thema Windturbinen, NNAISENSE, Drohnen und Deep Learning.
Thank you very much. Pleasure to be here.
Schöne Grüße in die Schweiz.